everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. In today's lecture, we'll discuss a completely new kind of centrality measure, which is very different from the degree centrality and also from the feedback-based centrality measures which we have been discussing, which would be the eigenvector centrality, the page rank centrality, or the Hobson authority centrality scores. So how exactly does this new kind of centrality work? Let's get started trying to understand it. As we already know, there are several kinds of centrality measures that one can use to rank the different nodes in a network. Just to list a few or categorize them, we know that in general, centrality measures can be ranked in accordance to the approach that they follow to rank the nodes. For example, we can have ranking based on the local importance of the nodes. Importance of the nodes. And the centrality that follows this approach is the degree centrality. Similarly, there are certain centrality measures which are feedback-based centralities. As you might have already guessed, the examples of this would be eigenvector centrality, Katz centrality, PageRank centrality, the Hits algorithm, or the Hub/authority centrality. So to those of you who are unfamiliar with this notation, it simply means that the term centrality gets repeated here, here, and here. There's yet another kind of centrality measure which we will discuss in today's lecture. Those are known as geodesic centralities or path-based centralities. This is the last topic in the area of centralities which we'll be discussing. What are the types of centralities which we'll discuss here? We'll discuss two kinds of path-based centralities. The first one is closeness centrality. And the second one is betweenness centrality. Let us try to understand how does each one of them work. So we start with the path-based centralities. And some motivation towards them. Why would we even look at path-based centralities? Let's try to figure out the motivation. First of all, how would we define a node to be central in terms of the paths is the first question. The second is, so in the motivation we'll answer two questions. The first is how, and the second is why. Why would we even want to do it? So the simpler question or the simpler answer is of the second part, the why. So let's start with an example of where path-based centralities become important. The image that is shown here is the image of the Silk Route. What is the Silk Route? Now, the Silk Route used to be an Asian trade route active from about the 2nd century BC until the mid 15th century. Now, this route played a crucial role as it connected the East with the West, meaning the route started from China and ended up extending up to the West, to the southern Europe. Why the term Silk Route? So it derives its name primarily from the highly lucrative trade of silk textiles, which are produced primarily in China. So this was the Silk Route, the route that is highlighted here. This was the Silk Route. Okay. Let us zoom in and look closely at the route that is shown here in the figure. So note that this trade was very lucrative, and hence this route in turn became a very important route. As I said, let us zoom in a little bit. If we see closely, there are certain nodes as marked here. Let's use a lighter color so that it becomes visible. Let us focus our attention on the two. So each vertex that is marked here is actually a place, a geographical location. So there's something very peculiar about the geographical location shown here and here. What is it? What is it that's peculiar? Let's see. Let's highlight yet another location, which is this. Now, fundamentally, the nodes in white and the node in green are slightly different. Why? Because now, while one is traversing the Silk Route, one could just simply take this path, which doesn't pass through the green node here. However, there will not exist a path which does not pass through this white node and this white node as well. Meaning, any path we take along the Silk Route, we were bound to visit certain nodes without fail. This example highlights that in certain cases or in certain applications, let's say, being centrally located in a geographical sense can offer advantages. So this answers the first part of two questions we had asked, which is why path-based centralities. So this is an answer of why it can be important to look at path-based centralities. Now, let's answer the second part of the question, which is the how of it. How would we go about calculating these central nodes, which are geographically important? In the particular figure that was shown here, it was very easy to figure out certain nodes of importance. However, in general, when the graph gets more intricate, it might not be so straightforward. So in those cases, how would we calculate these centralities? So in order to answer that, let's start by introducing the notion of a shortest walk. Shortest walk between nodes I and j. What is the shortest walk between two nodes I and j? It is simply the directed walk of smallest length. This is important. Length which starts at I and ends at J. Okay. This is what it is, the shortest walk between two nodes I and J. Now let us ask a few questions. The first question is the shortest walk unique? The answer is obviously no. A very easy example to see would be, suppose I simply construct a very simple structure like this. And 6. In this case, if I'm looking at the shortest walks from 1 to 4, there are two different walks which can be the shortest. One is this, the other is this, right? So the shortest path, obviously, which is very straightforward, need not be unique. Let's look at the other aspects. Associated with the shortest walk is the geodesic distance di to j. Now, what is the geodesic distance? Let's see. It is simply the length of the shortest walk from I to j. And as we saw, let's go back to this example. So obviously, there are multiple shortest paths that can be possible, but obviously the length in each case has to remain the same, meaning obviously the geodesic distance between two nodes is unique, which is again very straightforward. So we write it is obviously unique. Let's ask yet another question. Is the geodesic distance from I to j same as the one from j to I? Let's again look at another example. Let's construct a graph. Let's number them 1, 2, 3, and 4. What is the shortest distance in this graph? Let's bring it here. This particular graph in question, what is the shortest walk's length starting from 1 and ending at 4? So there's just one path here between them and its length is 3. So this becomes equal to 3. Similarly, what is the length of the shortest walk from 1 to 4? If we see here, there's just one walk and its length is in fact much shorter, equal to 1. Meaning, obviously, d1 to 4 is not equal to 4 to 1, right? But obviously, if I had chosen d2 to 4 and d4 to 2, both of them are equal to 2, and in this case, it would have become equal. So we can say di to j and dj to I are not necessarily equal. Let's define, after the short geodesic distance dij, let us define yet another term. which we will write as the geodesic between I and J passing through K. So what is this geodesic? Let's quickly define that. It says that for the nodes I, J, and K, all belonging to the vertex set, of course, Gi to K to J denotes the number of shortest walks from I to J which pass via K. It's simply the number of all those shortest walks originating from I, ending at J, which are passing through a certain node K. For example, if we go back to the same example which we discussed here, let me borrow the same example for this case. With this, we are ready to define the first path base or geodesic centrality, which is the closeness centrality. Let's get started. For a strongly connected network, strongly connected, say weighted diagram. The closeness the closeness centrality for the ith node is given by closeness for the ith node is given by this. It is the inverse. Let's first write it. J going to 1 to n. It is simply equal to the inverse of the sum of the geodesic distances which start from I and go up to every other node J, which are in the network. Okay, let's write it out. This represents the inverse sum over geodesic distances the I to J from node I to all the other nodes J in the network. So this is what it represents. Let us quickly see some examples of closeness centrality. Or let us first define what is something else that's known as betweenness centrality, and maybe together we will see some examples and compare the networks. So let me first define the notion of betweenness centrality. What is betweenness centrality? Again, or strongly connected weighted digraph. For the ith node, between a centrality is defined as follows. C betweenness I is simply equal to the summation of in the case of betweenness centralities, we are interested in figuring out those nodes I which lie in between all the geodesic paths. Meaning here I should write GK going from K to I to J. K is an intermediate node in the path where obviously K and J vary from 1 to n. And the betweenness centrality is a fraction. It's a fraction of what? Again, let's write out the same term. H, where again K and J vary from 1 to n. Now, we let H also vary over 1 to n, meaning H vary from 1 to n. Meaning, this basically gives us all of the geodesics that are there in the network. So what does this formula mean? This formula, or the score, centrality score, represents the fraction of all shortest paths basically, let's edit this slightly. It represents the fraction of the number of shortest walks. The number of shortest walks from any node K to any other node J, which pass via I. It is simply that fraction. So just to give you an idea, for example, in this network shown here, this would be my K, this would say be J, and I. Here, I lies in between. This is a shortest walk, and I is an intermediate node here. So basically, how many such times does I occur? A fraction of that represents its betweenness centrality score. So now let's look at examples to better understand both the closeness and betweenness centrality measures. Let us look at the network shown in this figure. If we look closely, we see that all of the walks that we design to start from this subgraph to every other subgraph that is there in the network will have to pass via node number 7. Hence, node 7 is betweenness wise central node in the network. In the network. Oftentimes, let's write it. Oftentimes, such nodes have the ability to serve as brokers between different groups. Different groups. Let us look at a few more examples. Let us now look at the network that is shown here. So if you look closely, then we see that there's a cycle in the network here. However, this is not the only cycle in the network. There's yet another cycle which goes like this. Let's mark the two cycles. This is the first cycle, and this is a second cycle in the network. Interestingly, it seems that the nodes 1, 2, and 3 are slightly more tightly connected as the rest of the network. Not only that, if you observe that whichever cycle that we draw here always passes through these three nodes. Owing to that, between centrality scores of all of the nodes in the network has an interesting pattern. That is, see betweenness, each of the nodes in the network, these values are equal to the nodes 1, 2, and 3, which are a part of every cycle in the network, have the same between centrality score given by 0.5. So what happens to the rest of the nodes, which obviously now may not be a part of every cycle that's there in the network, or might even pass through lesser number of geodesics? For them, the between centrality scores are equal to 0.35. Hence, there's a higher chance that the nodes which are shown here in the smaller cycle have a better chance of passing through all of the geodesics in the network than the nodes 4, 5, and 6, making them betweenness-wise central nodes. Okay. Because paths in a graph can always be symmetric. For example, one can take an all-to-all graph and try to calculate the betweenness and closeness centralities between all the nodes. It follows directly that all of the nodes will have the same betweenness and same closeness centrality values. Let's look at yet another example. This brings us to the end of this lecture on path-based centralities. As discussed, path-based centralities can help us figure out important nodes which can act as mediaries between two different subgroups in the network. In the next lecture, we'll discuss the Laplacian-based flows. So we have talked about the averaging model, and now we'll figure out what is the continuous counterpart of it, which is the Laplacian flow. Thereafter, we'll talk about more centrality-based notions that arise when we start using the Laplacian-based flows. Thank you.